0.174. Thank you, Bing. Okay, right. So the degrees to radians is multiplied by 0.0174, and that'll give you your whatever you've got in degrees. Times it by that number. It's actually longer than that. It's I put the whole lot. It's 45329. Right, and that works out. Converts to radians for you. If you do that, you will end up, when you plot your angle of attack, when you plot your coefficient of lift, and we'll do this in blue for thin airfoil theory, okay, what you'll end up with is, you'll end up with a line that kind of goes, I'm going to exaggerate it a little bit, okay, because it'll start with a 0 angle of attack there, and it works out something slightly different. In fact, I should have started that with at the bottom. But anyway, you'll end up with this, right? You'll end up with kind of line that goes like that. Because it's a linear equation, it doesn't change for, it's not a curved equation, right? It's a straight, the equation of a straight line, right? So that equation will give you that sort of thing there. So at some point, it will actually, just before the stall point, it will actually cross over with your, you know, with your lift, with your experimental data. Depending on the shape of your aerofoil, the difference here will be that large, but unless you've got a perfect thin aerofoil like the one I drew before, it's not going to match it exactly, and your answers for your coefficient are always going to be slightly lower than the coefficient in real life. Okay? Now, what we want is, so we're saying, alright, well that's, how do we modify that formula, how do we do that? Okay, so there was a dude called Prandtl came along, and what Prandtl said was, says, well, this theory here is for a finite wing, okay, a wing with no end. And we know that wings, at the end of the wing, I've just got my little model Spitfire here. Now, Spitfire wing is almost, well, it's not a perfect design, but it's very close to when it comes to induced drag. It was designed to minimise induced drag, okay? So the tips are very, it's called an elliptical wing, okay? But this isn't what the ellipse that we're talking about, not to be confused with an elliptical wing. We're going to talk about this elliptical theory of wings here, right? So nothing to do with Spitfire. What we're talking about here is we're talking about, we know from our studies that at the end of a wing you'll get induced drag caused by high pressure air underneath the wing mixing with low pressure air on the top of the wing and kind of leaking around, okay? And when it does that, it leaks around the wing, you get span-wise flow in both directions. So on the bottom of the wing you've got flow in that direction, the top of the wing you've got flow in that direction. Right, that span-wise flow, when it meets at the trailing edge, all the way along the trailing edge, you'll get vortices, not just at the tips, right? But those vortexes, right, combine. And what that does to our lift is, we find if we draw a picture of that, you find that you're getting that. So that's how much lift you've got in the centre of the wing. Towards the tip of the wing, because of the induced drag, you get less and less lift. Okay? Now, that means, if we use thin aerofoil data, that's for thin aerofoil, you can see that shaded area there, right, that's lift that we haven't got. Okay, so that lift there, that lift doesn't exist, there's not as much lift at the wing tips. So we need a theory like this which is going to incorporate some of the lost lift at the wings due to induced drag. Or due to lost lift due to vortexes. What we do is we end up with a modified theory which is the coefficient of lift is equal to 2 pi angle of attack in theta times aspect ratio divided by aspect ratio plus 2. What's aspect ratio? I hear you cry from YouTube land to say, oh, I've never done this before. Again, I'm not basing this on my students, I'm basing this on people watching this for the first time. Okay, so aspect ratio is how long and thin a wing is, or how the shape of a wing basically. A really good example of this is if you've got an F-104 Starfighter, both made by Lockheed, right? So if we do that, so there's your F-104 long, thin, pointy fuselage, probably a bit over exaggerated. It's got a T-tail on the back of it, sort of shape. Right, okay, and then you've got short stubby wings to make it nice and fast. It was one of the first American Mach 2 capable fighters. Okay, so that's a low aspect ratio wing. Now, exactly the same company, Lockheed, they also made a thing called the U-2, which is a spy plane or a reconnaissance aircraft. And if you just take those wings and your blues run out, sorry about that. If you just take that wing and you extend it out to there, make it long and thin, so there you go. That's called a high aspect ratio wing. Okay, so long, thin, stretched out wings are high aspect ratio, short, stubby wings are low aspect ratio, and you find them using this following formula. So aspect ratio is equal to the span squared divided by the wing area. Okay, so you work at your wing area in square metres, you work at your span in metres, you square that, divide by that, that'll give you an aspect ratio. Okay, so off the top of my head, I think if you have a span of 6 metres, a wing area of a chord of 1.5, so your chord is how far, you know, that's your distance there. Okay, we're just going to do a rectangular wing to make it easier for us. Okay, so a span of 6 metres, a chord of 1.5 will give you a wing area of 9 square metres. If you square that and divide that by that, you end up with an aspect ratio of 4. Okay, so again, if you put this into there, 4 plus 6, this is always going to be a number less than 1. Right, so this is going to be a factor less than 1. So I'll leave that aspect ratio up there, and that's what aspect ratio is. So if you then put Prandtl's lift and line theory into your, attach that to your thin aerofoil theory, what you'll end up is, you'll end up with a number that is less. This number divided by itself plus 2 is always going to be less than 1, isn't it? Yeah. So this factor that you're going to put in there is going to make sure that your, let's put it up in green. So we'll put Prandtl's lifting line theory, and what this will do to your graph, okay, you will have a line like that. Now, you might think, well, why have you done that? I've got further away from your results. You have got further away from your results, but if you look at your curve on here now, you'll find out like that your line follows your original experimental data a lot more accurately. So Prandtl's lifting line theory, once you add this little bit in here, okay, for your wing, should follow that, should follow your experimental data. It won't predict when it's going to stall, okay, but it will predict that for moderate angles of attack, for curved aerofoils, right, your Prandtl's lift line theory will follow a curved aerofoil profile a lot better than your thin aerofoil data on its own. Yeah, it's closer to what you'll find on experiments. You might think, well, why don't we just do experiments? So if you just do experiments on this, right, and you know how much lift you, so once you've got your, if we put standard lift equation in there again. So this is just to help you on your assignments, really, if you're asked to write an assignment about this, about kind of your understanding of how it fits into the big picture, about what you're trying to actually achieve with all these numbers, right? So if you put your CL and you've got your lift and you've got your half rho, sorry about that, your half rho V squared, right? So we know a wing area, we stick that in a wind tunnel, yeah, we work out the coefficient of lift, yeah, that all works great. But then we've got that coefficient of lift and we want to kind of get an accurate coefficient of lift so that when we get to higher altitude, possibly we'll be able to predict things like that. If we can't replicate high altitude on the ground, okay? So what you can do is you can use your theoretical data, right, for that aerofoil to say, right, well, this is the coefficient of lift I should be getting, right? And then if the stuff that you can replicate, in a wind tunnel, so let's say your density at sea level, you can replicate that, and velocities up to whatever your wind tunnel velocity will go to. Okay, remembering with your wind tunnel data, you're going to have to account for the fact you're going to get side turbulence off the walls of the wind tunnel. Your wind tunnel may be a Venturi type, so you have to work out your scale speed if you've got a very small aerofoil section in your wind tunnel. How is that going to, the air is actually going to be travelling faster over it with a smaller scale because it's covering more of the surface of the wing in the same time constant. So there's all sorts of things that you've got to account for. We're not going to cover that in this video, right? What we are going to cover is if you can't get to If you can't replicate high altitude, so you know that's 1.225 meters per kilograms per cubic meter at sea level. If you can't get less than the sea level pressure in your wind tunnel, and you want to see what your lift's going to be at high altitude, you can measure it. You get your coefficient lift at certain angles of attack, yeah, at low altitude, in your wind tunnel. Measure it, and then muck about with your figures on here and find out what that's going to be at high altitude. If you use your Prandtl's lift line formula, and then you work out the difference between your experimental results at low angles of attack and your theoretical data at low angles of attack, what you will come out with is, like, that distance there, if you use Prandtl's formula, may be a constant you can add on, right? So you use Prandtl's formula, you end up with your coefficient of lift, and let's say the red one, the one off the experiments, is, I don't know, 0.4, yeah? And then when you work it out using Prandtl's, you come out with the green one, which is this one here, and that comes as 0.3. You know fine well, you can then, and if you plot your data at low angles of attack at sea level density, at the velocities that you can achieve in your wind tunnel, right, then what you can do is you can work out your coefficient of lift for different angles of attack, right, compare them with your experimental data, stick them in there, yeah, and then you can say, oh well, my theoretical data is that, and then you'll find a constant, and that would be, that constant there will be, oh well they're all along this line, right, they're all 0.1 lower, yeah, they're all 0.1 lower. So you go, oh great, that's dead easy, that. So all we need to do is put in here, so to work on an accurate one for my aerofoil profile that I have done experiments with, right, my constant for that particular aerofoil, you stick that in, and then you can use this formula to work out your coefficient of lift all the way up to the stall point, and then you can then use this formula to stick into this thing here, change your density, change your velocity theoretically, yeah, so you haven't measured these velocities, these are just, oh hang on, if I was now doing, instead of 44 meters per second, if I was doing 140 meters per second, yeah, you can change that 140 meters per second, stick it into your formula and work out using your coefficient of lift that you'd work out from this, okay, for that angle of attack. And again, this angle of attack's in radians, I must stress. Then you would get your lift, how much lift that aerofoil will produce at those altitudes that you can't replicate in the wind tunnel. Right, gone off the track a bit there because I want to talk about drag. Okay, so that's the end of the thing about how to, that's two ways to calculate the coefficient of lift. Like I say, your thin aerofoil data will be closer to your experimental data, okay, in some parts, right, at some moderate angles of attack. If you modify it with this, you will always get less of a number. Your coefficient of lift will always be too low, slightly too low, but you can then modify that by working out your own constant based on your experimental data and adding your constant in to work out what that would be for your aerofoil. Now there's no real reason to do that for the BTEC assessment, or what BTEC expect you to understand at level 3. And I'm not speaking for BTEC, I'm speaking, this is my interpretation of what BTEC, what I think they're trying to find. They want to know, can you work out, can you find these equations, can you work them out, right, especially this one at the bottom end. I would be really happy with my students if they could work that out and say, right, this is different, yeah, because this theory doesn't match exactly what the experimental data is, and this is the reason why. Okay, the reason being that the theory isn't perfect. Okay, it'll predict the slope, right, more accurately, but it won't match exactly with what's happening in real life with air going over the wing. Right, that's the end of the thing about lift then. So bearing in mind, your theoretical coefficient of lift using this theory will not be accurate, okay, will not be accurate if you've got experimental data for lift and then you want to work out your drag, you're best off using that data. Right, we'll leave the aspect ratio up, we'll leave that on there. Now, working out your coefficient of drag, I'm going to use another formula on here. So your coefficient of drag, and this is based on Prandtl's lift line as well, is equal to CD, and I'm going to call this, how am I going to call this? CD par min. The minimum coefficient of parasitic drag. I'm not going to cover out the difference between parasitic drag and induced drag in this lesson, because I'm going to assume that you've done that already. And for this bit, just the top of my head, so we end up with this formula here, which is pi times E times aspect ratio. Now that E becomes important. Right, so this coefficient, I'm just going to put that on. Right, at this point, again, many thanks to not just these books here, but also there's an excellent website called www.aerospaceweb.org, and on that it has a point that which is a section that which is Ask a Rocket Scientist, okay, and that rocket scientist in question that answered this just give me 2 seconds.